In this video, we'll review how to integrate in spherical coordinates, how they're related to the other coordinate systems, and do a quick example illustrating these ideas. First, if I have a point in rectangular coordinates x, y, and z, I can relate it to spherical coordinates, which begin with the theta from polar coordinates. But instead of taking the distance r in the xy plane, we're going to take the distance directly to the point from the origin and call that rho. So the Greek letter rho is the distance from the origin to your point. And then finally, we need the angle that it forms with the positive z-axis. So the positive z-axis sweeping down towards that point, and that's the angle that we call phi. These three numbers, phi, rho, and theta, uniquely determine the point in spherical coordinates. In order to see how they're related to the other coordinate systems, it's helpful to take a radial slice of the picture that we have above. So suppose we've determined our theta. I'm going to look at the plane formed by this triangle here containing the z-axis along that ray that theta forms. And I've drawn that below, and I'm calling it the RZ plane. Clearly it's the z-axis here in the vertical direction, but that R is corresponding to the radial direction or the radial distance in polar coordinates along the bottom there of the projection of the point down onto the xy plane. If I redraw this triangle up above, I get the variables that I'm seeing in the coordinate system above. The angle phi here is just the angle in my triangle. The z-axis is running along here, so that's the z-coordinate. Rho is the hypotenuse of the triangle, the distance from the origin to the point itself. And then my radial distance in polar coordinates is r here. I've just drawn it at the top of the triangle right here, but it's the same as the radial distance there in the xy plane at the bottom. Armed with that picture, you can pretty much get all the relationships that you need. You know that polar coordinates relate x to r times cosine of theta. R isn't part of spherical coordinates. Theta is, so I need to convert just the r into an expression involving phi and rho, and I can do that using this triangle here. R is the opposite side, so it should be related to the sine of this angle phi, and if I use my standard trigonometric relationships, r is in fact rho times sine of phi. So I can replace the r with that expression, and I get this rho times sine of phi times cosine of theta. Notice it's two different angles appearing here in the trig expressions. A similar argument applies to y. Y is r times sine of theta, and we just determined that r should be rho times sine of phi times that sine of theta that comes from the y-coordinate. The z-coordinate is in the triangle as well. It's the adjacent side now. So if I take the cosine of phi, that's z over rho, and if I solve for z, I can now get the standard z-coordinate, the rectangular coordinate, in terms of the two spherical coordinates, rho and the angle phi. If you want to go the other way, if you know x, y, and z, and you want to find rho, rho is of course a distance from the origin to the point x, y, z, so you just sum up the squares, take their square root to find that distance. And the tangent of the angle theta is y over x, that's just from polar coordinates. And then cosine of phi, you can get whatever relationship you want. It's related to z over rho, just using the trigonometric expressions. If you want to integrate a function of three variables over a solid region, and you prefer to do that in spherical coordinates because it's got the appropriate kind of symmetry, the first thing you need to do is convert that function to a function of the three spherical coordinates, rho, theta, and phi. And then you'll integrate with respect to those three variables in whichever order happens to be convenient. And just as in polar coordinates and cylindrical coordinates, we get some factor of r, and in that case, that comes from that conversion. There is a conversion factor that we have to include when we convert coordinates, and that turns out to be rho squared times sine of phi. Now, that requires some sophisticated geometric argument to convince you that that's the right thing to include, And you should see that in your calculus course, or you can consult a textbook, but I won't go over that here just because it's a little bit complicated to do the geometric argument. So you have to take my word for it that's the right one, but you should have seen that at some point, or you should look it up in the textbook to see why that factor occurs. Let's look at an example. Suppose I want to integrate the function x, y, z is equal to z over the upper hemisphere of radius a. So what I'm going to do is take a sphere, put it at the origin, and I'm going to set the radius to be a. So a is some positive number, and I just want to take the upper hemisphere of it. So everything where the z coordinate is non-negative, so the top half of the sphere. And I want to integrate over that hemisphere the function z. The first thing I need to do is convert the function z to spherical coordinates, and using my relationships above, z is rho times cosine of phi. Because I'm converting to spherical coordinates, I get this factor of rho squared sine of phi. And then I need to make a choice of order of integration, and I've chosen d rho, d phi, d theta. Now, because I have theta outside, and I'm going to project everything down to the plane, and if I do that, I see that my theta must go through a range of values from theta to 2 pi. And if I sweep around that way, I will see something nice and symmetric, nice and spherical. I'm now going to fix a value of theta, a typical one in that range, and I'm going to take a radial slice. So what I'm thinking about is slicing that plane, including the z-axis, along that angle theta. And when I do that, I get something in what I call the RZ plane. If you think about that, for at least in one of the quadrants, that's going to be a part of that circular sector that gets carved out of the hemisphere. My angle phi starts at theta, starts along parallel to the z-axis. So when it's at phi equal to 0, I have a closed angle here along the z-axis, and then I have to sweep down to see the entire region, and that means phi has to go to a 90-degree angle, or pi over 2. And so my limits of integration for phi will be 0 to pi over 2. Now let's fix a generic value of phi. That's going to be some angle starting here at the z-axis and sweeping down. It's going to correspond to an angle of values of rho starting here, which is the distance to that point, which is of course 0, and moving out along the circle until the distance there is equal to rho equal to a. So when rho is equal to a, I'm a units in that distance right to the point, and that determines my limits of integration from 0 to a. In the next slide, we'll calculate this integral and actually find the value of it. So the same integral again, and let's at least simplify. I have 3 factors of rho, so I'll have rho cubed. And everything consists of constant limits of integration, so this should be very straightforward. I'm going to integrate with respect to rho. I'll get rho to the 4th over 4, and that needs to be evaluated between 0 and a. I plug in those numbers, and I'll pull out that constant, so it'll be a to the 4th over 4, and I'll pull that outside right away there. I now have to integrate sine times cosine. See if you can just guess what that antiderivative should be. One way to do that is to do a substitution. U is sine of theta, so du is cosine of theta, d theta. And if I do the integral of u, which is really what would happen after the substitution, I'll have 1/2 u squared. So what's going to happen here is I'll have 1/2 sine squared of phi. I need to evaluate that between 0 and pi over 2. When I plug in pi over 2, I'll have 1, so I'll get this factor of 1/2, and when I plug in 0, I get 0. And then we're just evaluating theta, and you've probably seen this quite frequently, where you're integrating, say, from 0 to 2 pi of just d theta, and so you're going to get a factor of 2 theta from doing that. And here's our answer, simplified.